In this video, we're going to put intermolecular forces to work as we talk about states of matter. Now, one of the pieces of information that gets passed on from year to year in schools is that there are 4 states of matter. In actuality, there are about 20 states of matter, and I say about because new states of matter are still being discovered. In talking about the 4 states of matter that get taught in schools, people are really talking about the 4 natural states, which are solid, liquid, gas, and plasma. In addition to the 4 natural states, there are 16 or more what are called modern or high energy states, but we're not interested in those in this chemistry class. In most chemistry classes, we're interested in solids, liquids, and gases. So we need some definitions. A solid is defined as something that has a fixed volume and a fixed shape. A liquid has the fixed volume, but it can take the shape of the container. Its shape can vary. In a gas, there is no fixed volume, there is no fixed shape, and as a matter of fact, gases will completely fill whatever container they're in. Now we need to talk about a particulate diagram. A particulate diagram is a model of a substance which shows how the particles are arranged to make up the substance. In using particulate diagrams for states of matter, you can see that for solids, the particles are tightly packed, they are held together quite strongly by intermolecular forces, and all they can do is vibrate back and forth. They can't move past each other. In liquids, you now have the particles being closely packed, so they are able to move past each other, and there are still intermolecular forces that keeps them cohesive. Gases, the particles are widely separated to the point where intermolecular forces do not have any effect, so they are totally free to move around the container, and that's why they completely fill their container. Now you can go from one phase to the other. Solid to liquid is called melting. Liquid to solid is called solidification. Sometimes it's called freezing, but I don't like that term because it implies a low temperature. Iron solidifies at 1500 degrees Celsius approximately. You would never say that the iron is freezing. Going from a liquid to a gas is vaporization. Gas to a liquid is condensation. You can go directly from a solid to a gas, and that's called sublimation. You can go directly from a gas to a solid, and that's called deposition. That one is usually forgotten about, but we deal with it here in New Hampshire all the time. Deposition is what happens when frost shows up on your windshield. Now we need some more definitions. The melting point, or MP, that's when a solid changes phase to become a liquid. The solidification point, or FP, and yes, FP stands for freezing point, that's the temperature where a liquid solidifies and becomes a solid. Now, under a defined set of circumstances, the melting point and the solidification point should always be the same. The boiling point, or BP, is the temperature at which a liquid changes phase to become a gas. Now, there's actually a little bit more to boiling point, but we will come back to that at a future lecture. For now, this will suffice. The condensation point, and I've never seen an abbreviation for that, is the temperature at which a gas changes phase to become a liquid, and under the same set of conditions, the boiling point and the condensation point have to be the same temperature. Now, melting, boiling, and sublimation, you heat up, so energy is added to the system, and adding energy to a system is the definition of what is called endothermic. Conversely, solidification, condensation, and deposition require that the substance be cooled, or you take energy from the system, and that is the definition of exothermic. So now let's combine phase changes and intermolecular forces. Intermolecular forces are one thing that influence the temperature at which phase change can occur. The stronger the intermolecular forces, the higher the melting point and boiling point will be. If you're asked to explain differences in substances between boiling point and melting point, what the question is really asking about is intermolecular forces. Because of that, you better name the intermolecular forces involved, and you better be sure that the answer goes with the data given. So let's have a few examples. The first, you want to know why butane, which has a molecular weight of 58, has a boiling point of 0 Celsius, and chloroethane, which has a molecular weight of 63 grams per mole, has a boiling point of 12 degrees Celsius, which is higher. The two molecules are similar in size, so they'd have similar LDFs. Butane is nonpolar, and it has only London dispersion forces. Chloroethane is polar, so it has the London dispersion forces and it has a dipole-dipole. The addition of the dipole-dipole will increase the intermolecular forces. The increased molecular forces holds the molecules together tighter. The tighter the molecules are held, the more energy it takes to separate them, and temperature being an indicator of the energy will be higher. What about this one, where nitrogen boils at 77.35 Kelvin, bromine boils at a much higher temperature, 332 Kelvin. Why? Both of these elements are diatomic. Both are nonpolar. The only intermolecular force here will be London dispersion forces. Bromine has more electrons than nitrogen, so it has a greater electron cloud, which means it can have a larger induced dipole. The larger induced dipole results in larger London dispersion forces, and therefore it takes more heat to vaporize the bromine than the nitrogen. And lastly, heptane, which has a molecular weight of 100 grams per mole, has a boiling point of 98 degrees Celsius, while ethanol, with a molecular weight of 46 grams per mole, has a boiling point of 78 degrees Celsius. Why the difference? Ethanol is polar, and as a matter of fact, can hydrogen bond, so you might expect it to have the higher boiling point. Heptane is nonpolar. Ethanol has London dispersion forces, dipole-dipole, and hydrogen bonding, and heptane only has London dispersion forces. However, the heptane has a much larger electron cloud than the ethanol. That larger electron cloud allows for a large induced dipole. That large induced dipole and the resultant London dispersion forces is greater than all of the intermolecular forces for ethanol, and therefore it has a higher boiling point. So you use intermolecular forces to explain the differences in those physical properties. So to review, there are three states of matter in chemistry that matter: solids, fixed volume and shape; liquids, fixed volume but variable shape; and gases, where both are variable. Solids, the particles are packed tightly and can only vibrate, and they have strong intermolecular forces. In the liquids, the particles are closely packed and can move freely. They have intermolecular forces acting here also. Gases, the particles are so far apart, there is no interaction between the particles, and they can move freely around the container. To go from one phase to the other is called a phase change. If it's endothermic, you have to heat it up, and that would be melting, vaporizing, and sublimation. Conversely, exothermic, where you have to remove heat and cool it down, is solidification, condensation, and deposition. The temperature at which a substance melts must be the same temperature at which it solidifies under the same set of conditions, and the same thing occurs with boiling point and the temperature of condensation. Differences in melting point and boiling point use differences in intermolecular forces. Better name the applicable forces, and the explanation must be consistent with the data. Just because a compound has dipole-dipole attractions or even hydrogen bondings doesn't mean it will always have the higher intermolecular forces when compared to another substance. So that's a brief introduction to solids, liquids, and gases. In the next video, we're going to talk about what's called the kinetic molecular theory, and with that, we'll be able to start our study on gases.